Good afternoon, everyone, and welcome to this Wine Australia webinar on the Climate Atlas. My name is Sharon Harvey. I'm a Research and Development Program Manager here at Wine Australia, and I looked after the project that delivered the Climate Atlas for us. With me in the studio, I have Belinda Bramley, our Extension Officer, and will be your production team for today. At the University of Tasmania, we have Dr. Rebecca Harris and Dr. Tom Remini, and they headed up the research team on the project that delivered the Atlas, and they'll deliver the webinar today. So just a bit of housekeeping before we start. The format will be a 30-minute approximately presentation by Beck and Tom, followed by a Q&A session of a similar length. So if you have any questions as we go along, please click on the chat button that you should see on your screen, and you can submit any questions to us. And we'll curate those in the background, and then they'll form the basis of the Q&A session following the presentation. We've also set up a quick poll, which should appear on your screen. This is just a simple yes/no answer, and it's just to give us some idea of how much engagement the audience has had with the Atlas prior to today. Please note also that this webinar is being recorded, and the recording will be made available on the Wine Australia website, where you're registered for the webinar following the conclusion of the webinar. So I think that's it for the housekeeping. So without further ado, I'd like to introduce Beck and Tom to present the Climate Atlas with a particular reference to the wine regions of Western Australia. Just to note that the intention here today is to present an overview of the Atlas and the information it contains, and to empower you with that information to go forward and make your own decisions on an individual and regional basis to work out how to manage the challenges that we're facing with regard to climate. So Beck's going to kick us off, so I'll now handball over to Beck. Thanks, Beck.
Thanks, Sharon, and thanks everyone for joining us. It's really good to see a really good turnout. We've changed it a little bit from yesterday. We're going to just be very brief introduction and spend a bit more time on the Atlas, and we've received some really good questions from you specifically about Western Australia, so we'll have plenty of time hopefully to talk about that throughout the talk and at the end in questions. So in terms of a bit of background, the wine sector, as with all other sectors, is going to be facing challenges as we go through into a warmer and drier world. We're looking at projections of up to 3 to 4 degrees relative to 1961 to 1990 by the end of the century, and that's under the emission scenario that we're currently tracking at the moment. So in recognition of this, in 2016, Wine Australia funded a research project which we led to consider the impact of climate variability and longer-term trends in climate on the wine industry. So that research project was a collaborative one that brought together researchers from a range of disciplines, including climate modellers, viticulturalists and people who were specialising in climate adaptation. And so we were aiming to provide Australia-wide climate information that was tailored for the wine sector and at a fine enough resolution to inform targeted adaptation responses within each of the regions. And we wanted to focus on the changes to timing and the length of the growing and harvest season and the frequency of extreme events such as heat waves. Information that we think is vital to plan for the future to reduce the impact of climate change. So Tom, if we go to the next slide, I think we have to actually share your screen. So what's in the Atlas? Basically, it's a summary of changes in the climate that we've already seen in the regions across Australia. If you go to the next slide, Tom, thanks. And the summaries are based on the most up-to-date climate projections at the finest resolution that's available across Australia at the moment, from 5 to 10 kilometres. And so there are maps that show the variability within and across all of the regions, and for every GI across Australia, there's a separate section, and it describes changes in temperature, rainfall, and the extremes of heat and cold, and aridity. So these indices were selected after talking widely with people in the wine industry, and we were hoping to choose widely used indices that are relevant to growing grapes. So if we go, so we haven't got time to talk all about these indices today, but just here you've got a list of them that you'll be able to find in the Atlas. And there are some really obvious ones, of course, growing season temperature, growing season rainfall, but there's also a couple of other indices that we've developed, for example, to have a look at the impact of heat waves on humans. And one of the things that I think was raised was how we adjusted the calculation for growing degree days. And that's a really good example of one where the industry accepted version of an index may not actually be all that usable in a warming climate. So, for example, starting in October, as we go forward into a warmer future, means that we might lose a lot of the early heat accumulation and miss those GDD units. The other thing we did with the growing degree days calculation was we took into account the fact that different base temperatures are applicable to different phenological stages. So we followed some of the literature there and adjusted that calculation. So we can talk a bit more about that in detail as we go forwards. Over to you, Tom. Sorry, I'm jumping way too quickly now. So I just wanted to add that, doing all of these things with the indices, it is fairly unavoidably and unashamedly a technical document. So you'll find at the beginning of every region a lot of detailed information on how we did the calculations and a how-to guide in terms of interpreting all of the graphs and details in the atlas. And then for those who might be slightly less interested in the details, there's also an infographic section, first page, which gives a quick summary of the climate changes expected at the different time periods for the region on average. Over to you, Tom.
Okay, so I think it's an important part of why the atlas was produced. And I'm going to quickly go through some really kind of basic climate science components. Apologies for those of you that already sort of familiar with this information, but I just think it's important to get everyone on the same page as to why this atlas is important and why Wine Australia are leading all the other industries in terms of producing this information. So carbon dioxide can be measured out of ice cores. We've got 800,000 year records of carbon dioxide, and we can see how it changes over time. Ranges between 150 and 250, 300, and at the present, it's jumped up enormously up to 400, so way outside of the paleo records paradigm. We care about this because the relationship with temperature is so strong. And in order to test this, scientists have been investigating and climate researchers have been investigating why this relationship exists for more than 200 years. The observations reflect that carbon dioxide has been increasing, and then so have the observed temperatures across the planet. All of these little ovals here are a little picture of the Earth, and I'm not sure why that other figure is not working, but anyway, it's a little picture of the Earth summarising all of the observed temperatures that we've seen since 1850, all the way through to present. And we can see that it starts off pretty white. There's not a lot of information available, but as we progress into more recent decades and years, we get higher and higher resolution information, and that information is clearly showing a strong warming trend into the future. In order to test the relationship between carbon dioxide and temperature, we need to build a model that can simulate the climate, something that we can use to, say, take out solar radiation, or add the volcanoes in and take the volcanoes out, and attribute the influence of those things to the climate system. This particular picture here summarizes all of the different components. Each one of them has tens to hundreds of equations inside the climate models, the simulations, and each one of those equations was developed by tens to hundreds of researchers over an entire lifetime. So this picture summarizes millions of human hours of effort into developing an understanding of how the climate system works. And this is what climate models look like. So climate models are dynamic, four-dimensional beasts. They have interactions with the landscape. So at every moment, all of these different equations are solved, and it shows where they will move next, whether they'll go up, whether they'll go down, that kind of thing. This image here is showing surface temperature and two cloud layers, a low cloud and a high cloud layer, and it's showing changes over a 3-hourly time step for the first 2 weeks of a model run. And it just demonstrates that these are very dynamic things. Taking the information out of this and converting into something that end users can use is an important part of our role, because it's not particularly useful to get to show you a video like this when you're trying to make decisions in a vineyard or in a winery. there's lots of observations of this throughout the world that show that the climate is warming. And we've got lots of different tests. Beck, did you want to take over from here?
I was actually going to say that we can refer back to yesterday's webinar where we went into quite a lot more detail about the experimental approaches that we use to attribute the human influence on the climate system. And these graphs, just if we flick through them fairly quickly, we can see that the observations show that there's been warming. If we run experiments where we only include natural factors, we're not able to replicate the observed warming. But we can only do that if we include the human activity, which you can see here in the pink. So I think we'll just flick through the next slide, which just shows that variability that is built into the climate models, and the fact that we understand the energy budget of the system. So we know that the human-induced greenhouse gases will far outweigh the natural variability in the system and the natural forcings. So we can think about these things on the global scale, but if we think about them at the local scale, we know that we're experiencing climate change. Sometimes thinking about the globe, it can be a bit removed, but we've been starting to see the impacts of climate change in our own lives more and more. So global mean temperatures have only increased by about 1 degree since 1910 or so, and that doesn't sound like much, but it has been enough already to start fundamentally changing the climate system. So recently we've seen the impacts of bushfires, heat waves, hurricanes and droughts all over the world. And all of these extreme events are occurring more frequently and with more severity and increasing impact. So we've seen temperatures start to rise above the physiological threshold of many species. But it's not just higher temperatures and changing rainfall patterns that we're talking about. The weather patterns are fundamentally changing as we go forward, and these impacts are expected to continue and accelerate, in fact. Over to you, Tom.
So this recognition of increasing extreme events has meant that the finance sector, insurers, banks that lend money for big investments, and the governing bodies have recognised that the market believes climate change is real and it's caused by burning fossil fuels. And they've released this document, Task Force on Climate-Related Financial Disclosures for big organisations who are in the stock market and have to give these kinds of things out in their prospectus, to provide guidance on what kind of information investors are asking for. It's prompted the Australian Prudential Regulatory Authority to have this statement in immediate response to this document, which came out some time ago now in June 2017. Company directors who fail to properly consider and disclose foreseeable climate-related risks to their business could be held personally liable. Now, foreseeable means not far-fetched or fanciful. The climate information has been well above that bar for more than 30 years, since the 1990s. And so for businesses to have not included climate change in their assessments of their future success or their future risks is actually something that potentially could make people personally liable. And there are cases in front of the courts around the world with regards to that. We'll skip over this one. If you want more detail, look at the work from yesterday, the presentation from yesterday for South Australia North. So we have endeavoured to use the finest resolution information available across the country. And as you can see here, that means that there's 5 kilometres over Victoria, 10 kilometres over the rest of southeastern Australia, and 50 kilometres elsewhere. I'll go into exactly what that means for Western Australia in a moment. There were 6 global climate models that we used inside this ensemble to present the mean and the range between them, and it gives a better idea of the range of possible futures using multiple models over the same region, using different assumptions. And so that gives us strong confidence. We selected those to particularly target the plausibility space and make sure that we got a good sense of, what happens if it was a wet model versus a dry model, or a cooler model versus a warmer model, and make sure that was incorporated. Oops, wrong direction. So for Western Australia, the finest resolution available, this is a representation of the actual topography at 3 kilometre resolution. We can see that there's very high heterogeneity in both southeastern Australia and Tasmania, where added high resolution information is incredibly important for making any kind of useful decisions. at every scale, all the way down to the paddock scale or even sub-paddock scale. In Western Australia, it's actually not anywhere near as much of an issue, and it's because the whole area is much lower in its overall height. And we can zoom in on that to show that. So that last one was showing just from 0 to 2,000 metres. This one's showing from 0 to 400 metres. And in Tasmania and Southeastern Australia, there's actually a dramatic, all this area goes white because it's actually outside of that zone. Whereas in Western Australia, most of the targeted regions are actually less than 100 metres or kind of edging up to 200. And that has that's a really important thing to keep in mind in terms of what does that mean for the validity of the coarser resolution information over there. It means that there's more validity over Western Australia than there would have been if we were operating over Tasmania, for example. Now, that's one example. What's one thing? We are aware of some higher resolution information at a spatial scale from Murdoch University. I'll look at the advantages first because these are the ones that Jarton has been expressing to the community over in Western Australia for some time. Higher resolution, both spatially and temporally, so doing smaller time steps and doing much finer resolution modelling space. It captures nuances around highly topographically varied regions. It improves detail at all scales. It has a much better representation of high intensity rainfall, particularly at the minute and hourly scales. It's much better representation of wind, the high intensity storms and things that come down, particularly those cyclonic systems that come down the west coast. And it has a better representation of extreme events of all kinds. There are some really big problems that we had with that that we needed to sort of overcome as well. So one of the ones is for the variables that we use in the atlas, which are actually mostly sort of annual scale or broader scale and 20-year time series climatological averages. There was less added value from high resolution information. There's also it was not temporally continuous or complete. It didn't have a complete baseline period for it to be consistent with the rest of the country. It didn't have a complete current period, so it wasn't consistent. We couldn't actually test the run as it was and compared to the changes that have already happened across the country over the last 20 to 30 years. It only had 4 of the 5 targeted time periods that we were using in the atlas, and it does not have any projections from 2060 onwards, so we weren't able to project out to that end of century. It was based on older scenarios and models, so it was an A2 scenario versus an RCP 8.5. It was CMIP3 models versus CMIP5, and it also used different GCMs. It had different model configurations and assumptions because it was based on WRF versus CCAM, and that meant that it had different boundary conditions and different parameterizations. But really, there was only one thing that stopped us from using it, and that was the absence of data for most of the time periods that we needed. As you can see from this figure right here, we only had a portion of the baseline period was available. Almost none of the current period was available. Only half of the near future was available from 2020 to 2040. We had all of 2040 to 2060, but nothing from 2060 to 2080 and 2080 to 2100. So in terms of trying to make a consistent product that was able to be to provide the same kind of utility to Western Australia as the rest of the country were getting, this data product just didn't allow us the capacity to use it because of this lack of continuous temporal periods. So really, out of all of those components, that was the really driving factor, that absence of data for most of what we needed. So now let's go into the actual atlas, and I'll let Beck talk to the current changes.
Thanks, Tom. Okay, so these maps show us the amount of change we've had in climate already. So we talk about the comparison between the current period, which we've defined as the period 1997 to 2017, and the historical period, which is 1961 to 1990. And it's really important to acknowledge that we are actually already seeing changes to the climate. So this map up the top is the changes in observed growing season temperature based on observations. And you can see that we have had significant warming up to about 0.8 degrees in some regions, and that's about the global average. But in other regions, particularly those that have a sort of a maritime influence, such as Tasmania and the south of Western Australia, we've had a lower amount of warming of about 0.4 degrees. So this map's really good, I think, because it shows us that variability across the country, but also within regions, we can see that the use of that fine-scale climate information is really giving us some added value. And at the bottom, we've got change in growing season rainfall, again, between the same periods. And you can see that rainfall is not as consistent across the country. It's increased in some regions and decreased in others. And this is obviously influenced by regional climate drivers that are affecting each of those regions, but it's also because rainfall is naturally highly variable across the country. And actually the climate change signal is not really expected to become clear for another decade or so. So if we go to the next slide, Tom, we can see the infographics that each section starts with. So for each GI, we start with this overview, which talks about the average across the region under the broad categories of rainfall, temperature, extremes of heat and cold, and then aridity. So in this example, we've got geograph. You can see that rainfall on average is actually projected to decline by quite a bit over the next few decades by the end of the century. And that's reflected in quite an increase in aridity as well. So the mean growing season temperature is projected to increase from about 19 degrees Celsius to about almost 23 degrees. So it's close to a 3-degree increase by the end of the century. Extreme cold also reduces substantially and extreme heat increases. And we can see that here with the extreme heat factor, which is an index that's used by the Bureau of Meteorology to describe heat wave intensity as it applies to human health. And it incorporates our ability to acclimatise to a certain extent to heat. Over to you, Tom.
So there was we've responded to some of the requests from your cluster that said to focus on different variables for different regions, and so that's what is here. Inside the atlas, we have these different pages. This is represented for the Swan District. We start off with the observed growing season temperature as we see it today. This is actually based on the Australian Gridded Climate Data product, which is an interpolation of actual observations. And using those actual observations, we can see how that changes over time from this current period and how much that has already warmed across the entire sector in the entire region since the 1960 to 1990 period. We then move into the projections themselves. We used a 50-kilometre grid that was bias corrected using observational data sets to make sure that we captured some of those features in the model, such as there's a ridge line that comes along here that you can see, and you can see that it has a very similar representation here as it does inside the model projections as a result of that. But then we still get those long-term changes, and that's much, I guess, best represented inside this time series. So here inside this time series, we can see that across the Swan District, it's relatively uniform. You compare that to some of the other regions that are presented in the atlas. There's not a big range of variability here compared to many others. That's due to a lack of topographic variability in comparison to some of the higher variable regions, such as some of those you'd see in central Victoria or Tasmania. But what it does represent very clearly is that interannual variability. So here we've got 2 years which are very, very different to each other, but sitting right next to each other. And with that occurred over the entire region. We've also put in place a warmer location and a colder location. So this sort of range of expected variabilities can be viewed as if you were sitting in one grid cell and how that was changing into the future. And here we can see that some of the colder regions are warming up faster than some of the warmer regions in this district, which is why that these two lines actually go from being, at least marginally different to each other here to actually being overlapping at this end of the time series. This is particularly useful for showing, say, extremely hot years and what that means. And these extremely hot years can actually be a little bit of a flag for the kind of conditions you should expect to see every year following a warming climate trend. And so that's a really nice one for growers to look back and say, oh, what did that year look like? 2016 is an absolute great example of that. being able to look back at those really warm years. What were the things we had to manage? What were the different challenges we had? And how many of those challenges are going to become things we're managing every day? So how are we going to build that into our operations? We can also see in the background here regions that represent other spaces across the country. And because the Swan District is the warmest region in the country, it doesn't have an analogue which it can look to into the future. But it does have an indication of exactly how much warmer it will get. And this might mean that Swan District needs to look internationally for other analogues, looking for those really warm places in maybe Spain or Italy, or maybe some of the warmer regions around the world. We can represent this information also as a probability distribution curve, and it allows us to see how that shifts forward into the future and whether that shape changes. And we can say at the moment there's very kind of consistent conditions year in, year out. Not a lot of variability along this axis here, where the warmer locations and the warmer years are clustered at this end, and the colder locations and the colder years are clustered at this end. As this drops into the future, it's indicating there's going to be more variability. We're going to get a bigger range of sort of really hot years and really cool years in comparison, although as you can see by 2100, the coldest years are actually the warmest years we see in the current period. This can also be described for different variables. This one's for the growing degree days instead of growing season temperature. And for obvious reasons, they have very similar curves and patterns, although this one's a little bit harder to see, but the growing degree days does have a little bit more variability in it than growing season temperature. Oops, my mistake. For growing degree days, as Beck mentioned earlier, it was crucial for us to incorporate all of this heat accumulation in the season from July to October in order to accurately represent when particular thresholds that were important phenologically were going to be reached in different regions around the country. Only using values from October, when we were already getting anecdotal evidence from some regions that a lot of flowering and the like was happening prior to October, meant that we just needed to use something that wasn't that standard October to April base 10. When we incorporated just the July to June, and so increasing it to the whole year, that certainly added some value, but we found that that wasn't really aligning with people's expectations because a lot of the July to October heat was being kind of ignored because of that base 10. And Beck mentioned this, that we used two different thresholds, which said that between 0 and 4 degrees, you were accumulating heat up until it reached a threshold of I think it was about 700 that was based in the literature. And then after that, it went from between 4 and 7. And then once you reached a threshold of about 1,000, it went from 10 and above. And this actually nicely flattened the curve, which made the growth a lot more linear, which was something that the viticulturists we engaged with thought was much more reasonable and reflected of what their expectations would be. And it also meant that it was now a nationally consistent growing degree day cap measure, which prior to that, a lot of those measures haven't really been particularly useful across the country, with some of the old school methods, say base 10, October to April, being not particularly useful in colder climates and not particularly useful in really warm climates because of the mismatch of some of those phenological expressions on the ground. This was important to us so that we could actually start testing the dates at which particular thresholds were being reached. And across the board, you can see there's a movement of about 6 weeks forward for each one of these thresholds, across, regardless of which one you choose. And that moving forward of 6 weeks, a lot of that occurs prior to October. So about 4 weeks of it occurs in that period prior to October, and then the subsequent 2 weeks is accumulated once the growing season really gets started. So this is now looking at Great Southern. and projections of rainfall into the future and that moisture balance. Again, we can see these the observed temperatures, the observed measures from the observed record and how that's changed into the future, with a bit of a drying at some regions and getting a little bit wetter over the last little while. And this will be interesting when I show you the impact that this moisture balance has had in comparison with temperature processes with regards to aridity. Over time, we can see there is a general sort of drying trend across the entire space, although it's fairly minor in the growing season rainfall, and this is reflected in the time series. The time series here can show.
Sorry, can I just break in for a sec? I think we can't see your cursor on the screen.
Oh.
It's important for these so we can see what particular graphs you're pointing at.
Okay, no worries. I will change that. So figure 1 is the observed growing season rainfall, and figure 2 is the observed change that we've already seen. And we can see in figure 3 that there has been a gradual drying trend across the growing season. However, when we look up at figure 4, the variability that you see between seasons is being maintained all the way out to 2100. So although that growing season expectation might be slightly drying over in a very kind of general sense, in a lived experience across the region, in that region, the amount of rainfall you expect to see across the growing season will be relatively similar similar to now all the way into the future. However, this is not the case when you look at figure 5 and you look at the non-growing season rainfall. There is a very great obvious trend of drying. It's been happening since about the 1970s or 80s, which is very similar to the trends that we see in Tasmania. This is due to the warming of the continent of Australia and the gradual shift of the subtropical ridge further south, pushing a lot of those rain-bearing synoptic systems further south so they don't make landfall. And that's a very well-known trend across particularly the Western Australian Southern Peninsula and also Tasmania. So that trend there is real. It's well understood, and it's projected to increase into the future as the climate warms. One thing I didn't talk about with the time series on the temperature range is why we've got these shaded zones in the bottom of these time series that are called greater than 1 degree C, greater than 2 degrees C, greater than 3. Those indicate the global climate temperature change that we should expect, global climate temperature change during those periods as projected by the current models. So, for example, in the period from 2050 to 2070, that's when the global climate models suggest that the whole world will be approximately 2 degrees warmer than today. That allows us to look at these figures not just with a time lens, but also with a temperature lens. So that if the global climate, if the global economic community and social communities decide that they really are going to take action on climate change, and therefore we limit our global warming to less than or about 2 degrees C, then we can look at that particular zone and say that's the kind of conditions we should expect over a much longer period. Similarly, if we fail to address and mitigate climate action, and actually do so even worse than what we currently are, then those greater than 3 or greater than 4 degree time periods could potentially come forward. And this allows this product to be used to see what those worst case scenarios might look like, and use that as a guide for what that means for organisations managing on the ground tactical and operational decisions. We've also presented this information in monthly rainfall in figure 6. Now what this is, it's called a violin plot. It's a probability distribution function, which is all of the values that you can see showing where they most likely occur. So the fat points on of these individual vases or violins, they are saying this is where most of the frequency of years occurred. So, for example, in the 2001 to 2020 time period in November, there is quite a broad base at close to zero. And that's showing that it's very dry in those conditions typically, but occasionally you can get rainfall over that period up to about 100 mils. And that's all based on the observations, that particular one. As we move into the coloured zones, that's where we're presenting the future climate change, and we've put the observations as a shadow underneath those, so you can see quite clearly how much the expected rainfall has changed inside each one of those months. And what this particular figure represents is that the rainfall changes are going to be most obvious in sort of April, May, August, September, October by 2100. So it allows us to look quite clearly at where those strongest changes will be. And although there is some change over the sort of the growing period of November through to March, those are nowhere near as significant as those you'd see elsewhere. We've also presented these as a proper probability distribution function in Figure 7, and again we've put the shadowed zones behind that so we can reference for different regions at different time periods across the year what they are going to be most similar to, and therefore they can look to those other regions to say, well, how will you manage that problem? In this particular context, we see very little change in summer, a bit of a change in winter and spring, and less change in autumn, but still there is a drying trend there. So there's drying trend in 3 out of the 4 periods. This also has an impact on the number of rainy days during harvest. And those rainy days during harvest are mostly being impacted when you get up to those higher GDD values. And that's partly because those higher GDD values are shifting from periods that are possibly a bit wetter now and moving into periods that are a lot drier as they move forward by 6 weeks. And that's what those rainy days at harvest are representing, is that kind of seasonal shift. It's a bit of an advantage in this context, because by 2100 you'll reach a threshold of 2500 faster, and as a result you'll get impacted by fewer rain events. So this is the aridity over Pemberton, and this is showing how there's a change in observed aridity. And this, I think we can kind of reference the Greater Southern observations a little bit in this, just to understand some of the interactions, where there's been an increase in heat, an increase in moisture, but we end up with a decrease in aridity, which means that we're getting, a more arid environment, which results in a lower value for this particular calculation. And this is the kind of thing we can see here, that it's more well represented in the atlas in general for each of these regions. And this is true across the whole of the country, is this general increase in aridity. We can see in Figure 3 that as we move forward from the current conditions into the future, even the next 20 years, there's going to be a relatively significant drying trend. And that drying trend, it just accelerates into the future for Pemberton particularly. This is one of the regions that actually dries out the most in this particular metric in the whole country. We can see there is internal variability. There's different, there's high years, wet years and dry years, but the general trend is definitely towards a drying environment. And where, Pemberton at the moment is a lot more like, say, Margaret River, and possibly even moving up into something similar to the Alpine Valleys of Victoria. But towards the end of the century, it's going to be a bit more like the Grampians or the Barossa Valley. So a very, very different environment. And this is an important direction of change for those people in that environment to consider in terms of different kinds of investment and mitigation options. It's very similar to some of the stuff happening in Tasmania as well. Again, we're presenting this in violin plots, which allow us to see exactly which parts of the season are having the most amount of change, or which full seasons are having the most amount of change. And for this particular region, it's across the board. There's very, very strong changes in every season, moving from very, very wet environments into much drier environments, all the way through. And this has a link to the amount of aridity that you would expect to see across an entire season as well, with a very an increasing trend of, or a trend of drying, which is what these aridity values represent into the future. Here we're presenting the data for Margaret River and showing how heat waves have changed over heat and extreme heat has changed over the last. So figure 1 shows the observed excess heat factor, this variable that Beck mentioned earlier. It's really a representation of sort of the severity of a particular heat wave. It has particular reference to humans, but it is very useful for understanding how that severity of heat, taking into account overnight temperatures and maximum daily temperatures, and what that means for the entire system that we live in. And although that one's focused on humans, it does have a fantastic capability of really capturing the severity factor, and that's what is being presented here. We can see that actually in Margaret River region, there's been a decrease in the amount of excess heat factor over the last 20 or 30 years. And so that might be, and that was actually reflected when we went and visited there, where although there might be many hot days, there were very few really, really intense heat waves over the last 20 or 30 year period. However, this is going to change, particularly into the future, with there being and at that southern tip of Augusta, where there's going to be an increasing severity of heat waves. So when they do happen, the conditions that are there that are causing that to happen are really kind of intensifying into the future. It is worth mentioning, though, that these values of, say, an excess heat factor of 15 are much lower than those that you would see over in South Australia. And that, I think, reflects the fact that in Margaret River, for example, in this example, it's moderated by the maritime climate, and the models really reflect that moderation in a large number of the extreme variables that we see for Margaret River, particularly given that it's bounded by 3 sides by the ocean. So that's one way. So I think I'll skip to figure 7 while we're talking about heat waves, and we'll look at how these overnight temperatures. So here we're presenting both the overnight minimums and the daily maximums. Now, while the daily maximums are very gradually moving forward, and that process has started with a really big jump expected after 2060, and that's probably going to be driven by some of the ocean warming, given the maritime climate. The overnight temperatures are, relatively, they've got very modest movements over the next 40 years, as projected here. But then there is going to be a dramatic shift with some really large overnight temperatures, really high overnight temperatures to be expected for some regions. And so watching out for when that particular type of condition starts to kick in will be an important metric for the Margaret River and probably a lot of southwest and Western Australia into the future, particularly moving past 2060. Well, you'll notice that the distribution of heat waves doesn't change very much, and this is because the way that they're calculated is based on the previous 30 years. So, or the way that these particular heat waves were calculated was based on the previous 30 years, which takes into account that humans and the organisms that are living there do have some capacity to evolve and to adapt. Not evolve, that's the wrong word, to adapt to the conditions over those long time periods. So if you've got 30 years, then the kind of expectations that you have, the behaviors that you have, the actual physiology of your body changes to be able to live with those kinds of conditions. And as a result, the timing of a heat wave, an extreme heat wave, is always going to be during the warmer months. And that's why that doesn't really move around very much into the future. However, that doesn't mean that we aren't going to get very, very extreme daily temperatures, as is represented by these heat wave representations here, and also by the figure 4, which shows projected number of extreme heat days. So days greater than 30, while at the moment sort of relatively, modest, less than 20 a year, sort of just edging up above that more recently as the climate change signal emerges from the noise of historical conditions. And then we're going to have a dramatic increase in that number into the future, where basically almost all of summer is going to be days greater than 30 by the end of century, and similarly much more dramatic increase in the number of days greater than 35. However, the maritime influence of this region is going to still moderate a lot of those very extreme temperatures, with very, very limited counts of greater than 40 or greater than 45 into the future. You can also represent that same information in figure 6, which shows the percentile range, and it shows that this the 90th percentile through to the 99th percentile for each of these time periods, and how all of these are gradually shifting up in a warming climate and slightly changing their shape. So this, for example, by 2100, the shape of this particular violin has moved a bit, where there is more of an expectation of maybe some of the warmer days than there was back here, which was a little bit more normal in its distribution. With so many warmer days, there's another part of this, and this is a big challenge for places that are moderated by the ocean. It's the combination of humidity and high temperatures. Combination of humidity and high temperature is well understood in Queensland, and it's less understood in southern Australia. But we can see here that Margaret River, for example, is already experiencing, and has done forever, a kind of baseline level of about 10 days a year when it feels really uncomfortable to work outside. And this condition of feeling really uncomfortable to work outside comes about when you have humidities greater than 60 degrees and temperatures greater than 30. We've projected how that's going to change into the future, and we can see that it's already sort of started. We would have expected to have almost a doubling of those kind of days already in the Margaret River region, and then that's going to just gradually increase and accelerate into the future. So this has a real importance on how workers are managed inside the wineries when they're out in the vineyards, what kind of infrastructure might be needed to keep people working during these kind of difficult conditions, particularly if we're getting up to the point where, 2/3 or the entire of summer is basically dangerous for people to be working outside without having some significant help. Not surprisingly, if you look at how much extreme cold there is in southwestern Australia, it's very low. There are very specific sites that might be exposed to extreme cold conditions, and for those particular locations, it'll be very important to understand that it's a decreasing risk. However, for most regions across southwestern Australia, it's not really much of an issue, and it won't be much of an issue into the future. It's a decreasing risk. And I'll hand back to Beck. I think I need a break.
I think you deserve a break, Tom. Thanks. So here we've got some of the rankings of each of the regions for different variables. So I probably won't spend too much time on this, but it's a good sort of introduction to the concept of climate analogues, which Tom sort of referred to. But perhaps if we go to the next slide, we can talk in more general terms about how analogues might help us plan for the future. We've been getting quite a few questions from people who are asking about what these climate changes actually mean on the ground. And I guess it's really important for us to sort of draw that line, that the Atlas is presenting the climate indices, and then it's pretty much sort of over to you to decide what you're going to do about it and what that actually means in terms of physiological thresholds for different grape varieties or access to irrigation and things like that. So the analogue approach, I think, is quite an intuitive way of thinking about that and starting to plan for different time horizons. So the concept really is just that you're trying to identify regions that are currently experiencing the conditions that you're projected to have in the future, and so that you might be able to learn lessons about how they deal with some of the climate challenges that they're already seeing. So I really love this plot. It's been a long time in development, and it gets tweaked and improved slightly all along the way. At the moment, we've got it so that you can see the round dot, which has which for every region. The tail in that line shows the climate change that we've already seen in each of those regions. And we're looking at an axis along the bottom, which is the aridity index that Tom talked about, so incorporating rainfall and evaporation. And then on the vertical axis, we've got the temperature. So you can see across the country, as you'd expect, a trend for all regions to get hotter and drier. So if we have a look, I think Tom's coloured the Western Australian regions in blue so that you can have a look. It's a little bit small for me, so I hope I'm going to get this right. But if we look at Pemberton, which is yesterday Tom's mouse was working so he could indicate it, but it's in the bluer side with the PB. And you can see that Pemberton hasn't really had an awful lot of change up until now. But as we go forwards into the future in 20-year steps, you can see that there's a period during which it might be more similar to the Hunter, and that it ends up being a bit more like what Perth Hills is currently experiencing now. And if we have a look at Margaret River, you can see that it has had more of a change climatically since the historical period. And it actually ends up being warmer and drier enough so that it doesn't really have any very close analogue regions, but it's sort of most similar to about South Burnett currently. If we look at Great Southern, you can see that it ends up towards a cluster which includes the Adelaide Plains or where the Riverina was in the recent past. So the idea with this is that we can have a look and try and learn and apply understandings and management options into the future. I think, as Tom pointed out, places like Swan Hill may end up needing to look overseas to find a climate analogue, and that's some work that we would love to spend more time doing, because it would end up perhaps with the opportunity of identifying perhaps new varieties that might be able to be applicable in the future across Australia. So in the interest of wrapping it up really quickly, I might just go to the summary where we've got three main take-home messages. And that is that we're already seeing changes in climate, and those changes are projected to continue across all of Australia and all of the world, of course. There are several trends in climate that are consistently found across all wine regions. They're all expected to get hotter and drier, more intense heat waves in many regions. Changes in rainfall is a bit more variable, but we can expect to see some change in seasonality in rainfall. And all of these things have widespread implications for the wine industry. And adaptation is going to be needed in the short and the medium and the long-term time horizons. And good information, good climate information that's been tailored for your industry and at as fine a resolution as possible is a really essential starting point for the future to plan. But it really is just part of that conversation, and it's a conversation that the industry now needs to take up to have a good, solid conversation about what sort of adaptation options are most applicable for your region. So just the final slide is just to thank the project partners, to acknowledge that CSIRO did the climate modelling, and we had Peter Heyman and Dane Thomas Paul Petrie from SARDI who helped us along the way. But we also are very much indebted to many of the growers in our case study regions, which included Hunter Valley, Grampians, Tasmania, Riverland, Barossa and Margaret River. And so those growers in those regions who really kept us on the straight and narrow and helped us really decide what indices were going to be most useful for you. Thanks.
Thanks, Tom and Beck. That's an awesome presentation. Hopefully everyone's now got a much better idea of what the Climate Atlas contains and how to extract information from it and how to use that going forward to plan the future for your region. We've had a few questions come in, so we'll run a quick Q&A session. If you're leaving us now, please link through to the survey that's going to appear in the chat page, as we'd love to have your feedback on today's webinar. Don't be shy, it's not too late to ask questions, so if something comes up in the discussion that you'd really like to know about, please send it through to us and we'll try and cover off on it. If we don't cover your specific query, please get in touch with us and we'll follow up for you. Our website link to our email address is about to also appear in the chat function. So Tom and Beck, I guess one question is, there are a few different emissions scenarios that have been posed. So how have you, can you sort of explain those and how you've built those into the Atlas?
I'll take this, Tom, if you're happy. So we've used, in the Atlas, we use the RCP 8.5, which is the high or business as usual emission scenario. And the reason we chose that, well, there was a couple of reasons. First of all, that's the scenario that we're currently tracking slightly above. And so that means that really for the next few decades, that's going to represent that very well. When you look at the slides that you can see in yesterday's webinar, where we spent a bit more time talking that through, you can see that actually those scenarios don't really diverge even between the high emission scenario and the lower one until about 2050, because there's a little bit of a spread anyway. So that's really why we selected 8.5. It's important to know that we do have a certain level of warming that's already committed in the climate system. So even if we were to stop all global emissions today, we are going to be dealing with rising temperatures for the next 100 or so years, 100 or 200 years actually. So the other thing we did was, which Tom referred to, was to try and superimpose those global mean temperature rises over the time series. And that's a way to sort of represent the potential for lower emission scenarios. So if you want to plan for us achieving our Paris Agreement goals, then you can look at those graphs and you can say, okay, let's look at where that 2 degree band is, and that means you can extract data and information at that point.
Awesome. Let me just have a scoot through. I think a few of these you've covered off on also. So I'm just having a quick look to see if there's anything else we can explore. So I guess a general question is, what do you think that the next steps are for grape growers and winemakers in the Western Australian wine regions to use the Atlas going forward?
So yeah, this is really the starting point of these discussions and that kind of idea of like where to next. You know, there's obvious discussions about what impact does this have on varieties, what impact does this have on management practices, and which of those can kind of be used in tandem to maintain existing conditions, or what do organisations want to do strategically into the future about, you know, who do they want to become? And I think it's an important part of the discussion for people to start considering that we can't keep looking back and say nothing's going to change. It is changing, it has changed, and it's going to change. So it's really about choosing which kinds of future each particular region wants, and each particular region, which values they want to focus on trying to preserve, and which values they are going to say, well, maybe we can change our values in that space. And that's an important part of the discussion. And that's not really our place to say that. It's our place to help guide. We can help guide those discussions. We can help use this baseline information and potentially even calculate new variables. We could calculate impacts on, say, smoke inundation. We could calculate impacts of biosecurity of various different types of pests for different regions. Those types of things could easily be done. But this is the starting point to say, okay, here's where we're at, here's where we're going. What are the things that are most important to this particular region? I guess, you know, if we had unlimited funds, let's do it all today. But, you know, with limited resources and time, what's the priority list? And that's what we really think that regions need to work as a community to come up with.
Can I just add to that, also to acknowledge that there was quite a lot of talk about adaptation in the Wine Futures project over the last 3 to 4 years. We did have a lot of conversations with wine growers in the sort of the case study regions, and you know there is a lot that's already happening to deal with bad years. So really, that's the point, isn't it? That we just know that those bad years are going to become more frequent. And so there's already a lot of talk going on all over the country. And I think, as Tom says, it's just a matter of really focusing those in and thinking about what time horizons people want to plan for, and thinking about, you know, what that actually means on the ground. And as Tom said as well, I think, of course, there'll be things where you'll say, oh, we wish we knew more about that. And some of that will be really basic physiological things about grapevines that is not, you know, that seems to be surprisingly difficult to or, you know, time consuming to find out. But others of it is really just about having a conversation and perhaps calculating some new things like, as Tom said, changing biosecurity, bushfire risk, that sort of thing.
Mm. Yeah, thank you. And I think it's probably worthwhile pointing out at this point that Wine Australia is here to help with those conversations. It's not something that has to happen quickly. No one needs to do anything today or tomorrow or next week. It's going to be a bit of a journey that we can go on together. And don't be afraid to reach out and contact us and let us know how we can support you through that and through your decision making and what comes next as we adapt to our changing climate.
Yeah, I think just on that too, Sharon, there's two ways of thinking about these kinds of challenges. One is in that kind of adaptive space about what are the things that can change behaviour to maintain the current conditions. And then the other is really that kind of like much strong, so that's like, you know, changing your vine management practices to increase shading or to use sunscreens or those kinds of things, which isn't really changing the core business, but it's making it possible to continue doing those for a longer period of time. And then there's the things that, like, no, we really need to change the whole way that we operate. So, you know, do you do dry land growing, and or are you going to have to start thinking about introducing irrigation because rainfall patterns are changing to the point where it's no longer sustainable to stay a dry farming approach. And these kinds of decisions are in very different time horizons and different spaces. And it's about starting with the ones that are kind of easier to get into that mode and then transitioning into those other more difficult conversations later on.
Mm. Okay, great. I think given the time, we might round things off for today. So that concludes the webinar for WA. Just a reminder that this webinar has been recorded and it will appear on the Wine Australia website shortly after the conclusion. You can also access it via the Wine Australia website, and we've also provided links to the final report, the ABC landline story, and also the Climate Atlas itself, obviously. And you can extract the regions that are important to you and download those individually. We've also posted all these links to the chat, so you can link to them there. You'll receive the next step also is that you'll receive a follow-up email with all these links and pointing you to the survey if you haven't got to it today. I think that pretty much concludes the session for today. Thank you very much to those who attended, and see you next time.